Okay, so today we're going to keep talking about this transient numerical simulation. This is something we started last time. We went through these steps. We distributed a bunch of nodes throughout our computational domain. We carried out an energy balance on each node, and the main result of that was this set of state equations, which I've listed here, one for every node. And then we are now talking about different ways that we can integrate this set of state equations forward through time. So these are the state equations that are associated with this problem over here, which is a fin that's starting up from being in equilibrium with its surroundings. All right, so last time we talked about Euler technique, which is a pretty easy technique. It's an explicit technique, and it's first order. So today we're going to talk about some more advanced techniques, and the more advanced techniques kind of fall into two categories. One is implicit and the other is higher order explicit techniques. So let's talk about predictor corrector techniques, which are higher order explicit techniques. And we did this when we were talking about lumped capacitance problems. We had Hoyne's method, and we also did the Runge-Kutta fourth order method. So we're gonna do Runge-Kutta fourth order method for this problem because I think it's a pretty nice method to know about. So Runge-Kutta fourth order method is it's fourth order, which means, if you remember, that there's going to be 4 predictor steps, and then we're going to take all that information together and do a corrector step, which is how we finally predict our temperature at the end of the time step, right? So there's going to be 4 steps to getting through the time step, and really the sort of details of the technique boil down to how do you take those predictor steps, and then how do you combine that information to get a corrector step. So we are going to write a program or a function that will provide these state equations given a value of time and the values of all of the temperatures, and that's just making it very easy for us to sort of do those calculations automatically. So the first thing we're going to do is write that function. I'm going to implement this in MATLAB. So here's my function in MATLAB that does that. I called it lecture 19 because that's about where we're at. It takes in time, so that's just a number, which is what time is it in your simulation, and then this t is a vector of all the temperatures, and it goes through, and down here you can see it just implements those state equations, right? So it's going to return then a vector of all of the time rates of changes for each of these temperatures, right? So that's our function. That's going to be the engine that sort of runs the RK4 technique. Once I have that function working, then it's just a matter of actually understanding how Runge-Kutta fourth order works, right? So here's the whole idea. I'm coming into a time step. At the beginning of the time step, I know that the temperature of all the nodes, and I know the time. And the whole point of the algorithm is to predict the temperature of all the nodes at the end of the time step, right? So how we do this is with 4 predictor steps. So the first thing we're going to do is calculate the time rates of change of every single node evaluated at the beginning of the time step, right? So here I'm at the beginning of the time step. I'm using the temperatures at the beginning of the time step. I'm calling that function I wrote, and I get this vector, we'll call it AA, which is just d-temperature, d-time for every node. So AA is, if I want to put it on this map, it's sort of the time rate of change evaluated right here at the beginning of the time step. And then I use that to take my first predictor step. So my first predictor step is just using these time rates of change to predict what are the temperatures of every node at the center of the time step, right? So I take those time rates of change and I multiply by delta t over 2. And that gives me a vector here of temperatures at the center of the time step, right? Halfway through the time step, this is a good estimate of what the temperatures are. And then I use those temperatures to predict the time rate of change at the middle of the time step. So I'm using these temperatures that I just calculated, and if anything is a function of time, Of course, I'm using the right time, right? I'm using the time right here in the middle of the time step. So that's going to be BB, right? That's an estimate. BB is an estimate of all the time rates of change at the middle of the time step, right? So the next thing I'm going to do is actually estimate again the temperatures at the middle of the time step. So here I'm doing the same thing I did here. I'm doing it here. The only difference is now I'm going to use BB instead of AA, right? So here I estimated the temperatures at the middle of the time step using this set of temperature derivatives. Here I'm going to estimate the temperature at the middle of the time step using this set of temperature derivatives, right? So I have now another set of estimates of all the temperatures at the middle of the time step. It'll be slightly different than this set of estimates. I don't need these temperatures because they're just intermediate variables, right? And I use that set of temperature estimates to get another estimate of what are the time rates of change of all the temperatures at the middle of the time step, right? So now I'm using my most recent set of temperatures at the middle of the time step. And again, if anything's a function of time, I'm going to use it at the center of the time step. So this is CC. This is a vector of all the time rates of change at the middle of the time step. And then the last thing I do is use this vector of time rates of change, CC, to estimate what are the temperatures at the end of the time step, right? So now I'm taking a full time step. That gives me another set of intermediate temperatures, and I use that to calculate DD, which is my estimate of what are the time rates of change here at the end of the time step, right? So I'm using all these temperatures that I just estimated at the end of the time step, and if anything's a function of time, I'm going to evaluate that at the end of the time step too. So the outcome of this is that I have four estimates of the time rate of change for every temperature, right? I have a set at the beginning of the time step, I have two sets at the middle of the time step, and I have a set at the end of the time step. All right, so now I have to take that information that I collected, so this is my information I collected during my predictor steps, and I have to combine it somehow to finally take my corrector step. And my corrector step is what's actually going to predict the temperatures at the end of the time step, right? And the way we do that here, sorry, this should have an over bar because this is a vector of temperatures. The way we do that here is we combine those slopes according to this equation here. Right? I take 1/6 of this slope, 1/3 of this slope, 1/3 of this slope, and 1/6 of this slope, right? I'm just weighting these different slopes by a different amount. Multiply it by delta T, and that gives me my temperatures all at the end of the time step. And this is extremely accurate, right? This is fourth order accurate. It's still explicit, so no more stable than Euler's technique was, but very, very accurate. So to see how we did this in MATLAB, this is my RK4 technique. 21 nodes. I'm going to take 500 time steps. I'm simulating 50 seconds. And then this is all there is to taking each step, right? So here I know my initial condition, all of the temperatures are T infinity, and then this should be exactly what we just talked about in the previous slide, right? This is AA, and I get it very easily by using this function that I wrote where I give it time and all the temperatures. I get T hat, so this is a vector of temperatures at the middle of the time step. BB is evaluated using that vector of temperatures. I use BB to get another T hat, right? I'm just overriding T hat because it's just an intermediate variable. I don't care about it after I use it. CC, DD, and then this is my corrector step, right? And if I run this, somewhere I should get a plot, which I'm not seeing right now. Oh, here it is. So this is temperature as a function of time, temperature as a function of time, and then this is each of my nodes, right? So same solution, just more accurate. It's a more accurate way of doing it. Okay, so well, that's predictor corrector techniques. So that's an explicit technique still, but higher order. If you want to go to an implicit technique, the easiest implicit technique to think about is the fully implicit technique, right? So the fully implicit technique looks a lot like Euler's technique, right? In Euler's technique, we evaluated the temperature derivatives at the beginning of the time step, which is a place where we knew everything, so this became an explicit equation. For the fully implicit technique, we're going to do the same thing, but we're going to evaluate the temperature derivatives at the end of the time step, right? So j plus 1 and j plus 1. And what that means is now I'm going to have a big set of implicit equations, right? And it's pretty easy to do this in ease, right? And again, I would sort of recommend you take the first step, and then you take all the steps. So let's look at the ease file. So here's the ease file. Basically what I did is I just copied the Euler technique file, and I just changed these parts of the file here where I'm calculating the derivative. So previously I had j, which was the beginning of the time step, and instead I just put in j plus 1. And this is an implicit technique then, right? So I can get rid of that. I can run this, and I get a solution. My critical time step is 2.5 seconds. I have a solution that's stable. You can see it's stable. In fact, you can look at it here. It looks like this. Even if I take fewer time steps, so I have a larger time step duration, right? So now I am taking 5-second time steps, even though my critical time step is 2.57. What you're going to see is my solution is still stable, right? It's not as accurate, but it's still stable, and that's the main advantage here of the implicit technique. If I want to move the implicit technique into let's look at this one here, I guess. If I want to move the implicit technique into a formal programming language, it becomes a little bit more tricky, right? So here's my set of equations that I have for the fully implicit technique, right? This is, let's look at node 1 here. This is node 1 at the end of the time step, node 1 at the beginning of the time step, and then this is dTdt evaluated at the end of the time step, right? And I don't know these temperatures at the end of the time step, so this is no longer an explicit equation. Same thing here for these internal nodes and this one for node n. So I end up with a set of n equations, right? This is n equations in my n unknown temperatures at the end of the time step, right? So T1 through Tn j plus 1. I do know T1 through Tn at the beginning of the time step, but I don't know them at the end of the time step. So this is something that I'm going to have to solve somehow, right? And we can solve it the same way we talked about before. We can do matrix decomposition, or we could do Gauss-Seidel iteration, however you're most comfortable with. I'm going to solve it here using matrix decomposition, which means that I'm going to put it into this format right here, right? We said that this A, that's my coefficient matrix. These are where all the coefficients go that multiply all of my unknowns. X is my vector of actually unknowns, so when I get done, I've predicted X, and then B is my constant vector, right? That's where all the constants go in my equations, right? So the only trick then is I have to have some order to how I'm going to put the equations into A and B, and there's only one really that makes any sense, which is I'll start at 1 and go to n. And I have to have some order for how I'm going to put my unknowns into X. And again, it really only makes sense to start at 1 and go to n here. So with that, then, I know that, when I'm putting in coefficients, the row corresponds to the equation number and the column corresponds to the unknown number, right? And so if I just keep that in mind, it becomes pretty easy to put these equations into matrix form, right? So that's what I've tried to do here. I started with equation 1. It's easiest if you rearrange it so it's clear what are the coefficients multiplying the unknown and what's the constant. So here's an unknown, here's an unknown, here's an unknown, and here's an unknown, right? So let's see what the coefficients multiplying the unknown is. So here I have T1 j plus 1. I have pulled together all the coefficients. So here's a 1. Over here, if I bring it to the other side, I have a plus 2 alpha delta x squared times delta t. And here I have an h bar perimeter times AC over rho c times delta t. So there's a coefficient. Here's another unknown, T2. The coefficient multiplying it is right here. And then everything else is a constant, so I just leave it on the right-hand side. So this is very clear then where I got to put these parts of this equation, right? This is a coefficient. This is the first equation, so this coefficient is going to go in row 1, and this coefficient is multiplying the first unknown, so it's going to go in column 1. This is a coefficient, so it's going to go in the A matrix. It's still in equation 1, but now I'm multiplying unknown 2, right? And then finally, this is a constant. So this constant is going to go in the B vector, and it's going to be the first element because it's the first equation, right? This is all my internal nodes, same process, right? I'm just finding all of my unknowns. There's a bunch of them here. I bring them over to the other side and figure out what all the coefficients are, and then whatever's left over is a constant. So every one of these is going to go into the ith row, right? And then it just depends on which unknown is it multiplying. So this is the ith unknown. This is going to be ai. This is the I minus 1 unknown, so this is ai I minus 1. This is the I plus 1 unknown, I plus 1, and then this is bi. And then finally this is node n, right? So that's the last one to do. And at that point, I've completely constructed A, and I've completely constructed B, and then it's very easy to get all of your T's because it's just the inverse of A times B, or better yet, A backslash B if you're using MATLAB. So let's have a look at that, if I can find it here. So yeah, this is my code for the implicit technique. I'm going to take 200 time steps, 50 seconds, my initial conditions here, and then here I have to set up my A and my B vector. And actually, if you look at what's going on here, it's kind of interesting. All the coefficients for this problem, and this problem is kind of a simple one, but all the coefficients are the same for every time step, right? They never change because they don't depend on temperatures, right? So as a result, for this particular problem, I can set up A one time, and that's what I've done here, never have to change it again. What changes with every time step, though, is my B coefficient, right? Because that's always going to depend on the temperatures at the beginning of the time step, right here, and then also right here, right? So I have to reconstruct B every single time step. So that's why it goes inside of my for loop. So here I'm building B. That's what these equations are. I get X is A backslash B, so that's getting the temperatures at the end of the time step, and I put them into a big matrix, and then I just repeat, right? And I can look at the solution. I can look at it by plotting it. I can actually look at it by making a movie, which is kind of cool here, let's change this to 400 in MATLAB. So let's run this, and somewhere I should be able to see a movie. Yeah, so you can watch my fin temperature distribution evolve there, right? So this is temperature as a function of position, and it's changing with time here, right? And that's kind of cool, actually. I can turn that movie into an AVI and embed it into different presentations and things like that, right? But I'll play it again. So starts at T infinity, and then you can see, this slope here is always the same because I have a constant heat transfer rate. The tip is adiabatic, and then you can watch this thing evolve. And actually, this is a good place to stop for a second and think about what's going on physically and how much of this solution we could have anticipated before we even started working on a numerical model.